calculation for voltage drop appears to be correct, indicating that 2 American wire gauge wire is needed for a 50 amp load over 300 feet to maintain a voltage drop under 3%. One potential solution to consider is a special, though unofficial, method for running underground feeder cable when using large conductors. The first step involves digging a trench that is 2 feet by 2 feet. After excavating the trench, place 6 inches of sand at the bottom. Next, fill the trench completely with water. Then carefully roll out the underground feeder cable within the trench, ensuring that you do not cut it to its final length. Leave a coil of approximately 20 or 30 feet of underground feeder cable at each end of the trench to allow for connections. After positioning the underground feeder cable, backfill the trench with at least 2 feet of wet dirt, thoroughly tamping it down to create a mud bath. Allow the ground to dry and harden completely. This process seals the underground feeder cable in place, preventing movement. Finally, dig a small hole near each end of the trench. Pull out enough of the coiled underground feeder cable to make the necessary connections to the devices and splice the other end of the underground feeder cable to the feeder cable. Backfill the holes with dirt to complete the installation. The idea behind this method is that the sealed underground feeder cable in the mudbed will act as if it were installed in a conduit. The water will also prevent oxidation of the underground feeder cable and help to dissipate any heat generated. While this method is not officially recognized, it has been reported to work effectively. Other methods you might consider: firstly, running a larger diameter conduit such as 3-inch or 4-inch and pulling 2 number 1 American wire gauge or 2 number 2 American wire gauge conductors through it. Secondly, running 2 separate trenches and burying 2 smaller diameter underground feeder cables, each containing 2 number 3 American wire gauge or number 4 American wire gauge conductors. Selecting the appropriate wire size for electrical installations is crucial to ensure safety and prevent voltage drop. Voltage drop occurs when the voltage at the end of a conductor is less than the voltage at the source. Excessive voltage drop can lead to inefficient operation of electrical equipment, overheating of conductors, and potentially hazardous situations. Several factors influence voltage drop, including the length of the conductor, the current flowing through it, the conductor's resistance, and the voltage of the source. To calculate voltage drop, you can use the following formula: voltage drop equals current multiplied by length multiplied by resistance divided by number of conductors multiplied by 1000. The allowable voltage drop is typically specified in electrical codes and standards, such as the National Electrical Code. The NEC recommends a maximum voltage drop of 3% for branch circuits and 5% for feeders. These limits are intended to ensure that electrical equipment operates within its design voltage range and to prevent safety hazards. To minimize voltage drop, you can take several steps. Firstly, increase the conductor size. Larger conductors have lower resistance, which reduces voltage drop. Secondly, shorten the conductor length. The shorter the conductor, the less voltage drop there will be. Thirdly, increase the supply voltage. Higher voltage systems experience less voltage drop for the same amount of power delivered. Fourthly, use conductors with lower resistance. Materials such as copper has lower resistance than aluminum. Fifthly, reduce the load current. Lower current reduces the voltage drop. Conduit is a protective raceway used to enclose electrical wiring, providing mechanical protection and a path for running conductors. There are several types of conduit available, each with its own characteristics and applications. Rigid metal conduit, or RMC, is a heavy-walled, threaded conduit typically made of steel or aluminum. It provides excellent mechanical protection and is suitable for both indoor and outdoor use, particularly in harsh environments. Intermediate metal conduit, or IMC, is a thinner-walled version of RMC, making it lighter and easier to work with. It offers good mechanical protection and is commonly used in commercial and industrial applications. Electrical metallic tubing, or EMT, is a thin-walled, unthreaded conduit made of steel or aluminum. It is lightweight and easy to bend, making it suitable for indoor applications where mechanical protection is not a primary concern. Flexible metal conduit, or FMC, is a spiral-wound, flexible conduit made of steel or aluminum. It is used to connect electrical boxes, and equipment in tight spaces or where vibration is present. Liquid-type flexible metal conduit, or LFMC, is a flexible metal conduit covered with a liquid-type plastic jacket. It is used in wet or damp locations to protect conductors from moisture. Rigid polyvinyl chloride conduit, or PVC, is a lightweight, non-metallic conduit made of PVC plastic. It is resistant to corrosion and is commonly used in underground and wet locations. Each type of conduit has its own installation requirements and limitations, so it is important to select the appropriate conduit for the specific application. The National Electrical Code provides detailed guidelines for conduit installation, including support requirements, bending radii, and grounding procedures. When selecting conductors for electrical installations, it is important to consider several factors to ensure safety and compliance with electrical codes. Firstly, ampacity is the maximum current carrying capacity of a conductor, expressed in amps. The ampacity of a conductor depends on its size, material, insulation type, and installation conditions. The NEC provides ampacity tables that list the allowable ampacities for various types of conductors under different conditions. Secondly, voltage rating is the maximum voltage that a conductor can safely withstand. The voltage rating of a conductor must be equal to or greater than the voltage of the circuit in which it is used. Thirdly, insulation type is the material that surrounds the conductor and provides electrical insulation. Different insulation types have different temperature ratings and resistance to moisture, chemicals, and abrasion. Commonly used insulation types include thermoplastic high heat resistant nylon or THHN, thermoplastic high water resistant nylon or THWN, and cross-linked polyethylene or XLP. Fourthly, conductor material is typically copper or aluminum. Copper has higher conductivity than aluminum, but it is also more expensive. Aluminum conductors are lighter and less expensive than copper conductors, but they require larger sizes to carry the same amount of current. Fifthly, environmental conditions such as temperature, moisture, and exposure to chemicals can affect the performance and lifespan of conductors. It is important to select conductors that are suitable for the specific environmental conditions in which they will be used. Sixthly, the National Electrical Code provides detailed requirements for conductor selection, including ampacity correction factors, dirting factors, and grounding requirements. It is important to consult the NEC and other applicable standards when selecting conductors for electrical installations. Underground feeder or UF cable is a type of electrical cable specifically designed for direct burial underground. It consists of two or more insulated conductors surrounded by a moisture-resistant outer jacket. UF cable is commonly used for underground branch circuits and feeders to supply power to outdoor lighting, receptacles, and other equipment. One of the key advantages of UF cable is its resistance to moisture and corrosion. The outer jacket is typically made of a durable plastic material that protects the conductors from water, chemicals, and other environmental factors. This makes UF cables suitable for direct burial without the need for conduit in many applications. However, it is important to follow the manufacturer's instructions and local electrical codes when installing UF cable. Proper burial depth is essential to protect the cable from physical damage and ensure safety. The NEC specifies minimum burial depths for UF cable depending on the voltage and location of the installation. Typically, UF cable must be buried at least 12 inches deep in residential areas and 18 inches deep in commercial or industrial areas. In areas subject to vehicular traffic, the burial depth may need to be increased to provide additional protection. When installing UF cable, it is important to avoid sharp bends and kinks, which can damage the insulation and reduce the cable's lifespan. It is also important to protect the cable from rocks, roots, and other sharp objects that could puncture the outer jacket. One way to protect UF cable is to bed it in sand or fine soil before backfilling the trench. Another option is to use a protective sleeve or conduit in areas where the cable is exposed to potential damage. When splicing UF cable underground, it is essential to use waterproof connectors and sealing methods to prevent moisture from entering the splice. Direct burial splice kits are available that provide a reliable and watertight connection. It is also important to properly ground the UF cable to protect against electrical shock hazards. The grounding conductor should be connected to a grounding electrode system, such as a ground rod or grounding plate. The size of the grounding conductor must be appropriate for the size of the circuit conductors. Voltage drop is a critical consideration in electrical installations, especially over long distances. Excessive voltage drop can lead to dimming lights, reduced motor performance, and overheating of conductors. To minimize voltage drop, it is important to select the appropriate conductor size for the length of the circuit and the amount of current it will carry. The NEC provides voltage drop recommendations and formulas for calculating voltage drop in electrical circuits. In general, it is recommended that the voltage drop in branch circuits should not exceed 3% and the voltage drop in feeders should not exceed 5%. To reduce voltage drop, you can increase the conductor size, shorten the circuit length, or increase the supply voltage. Conduit provides mechanical protection for electrical conductors and can also help to prevent voltage drop by providing a path for heat dissipation. When installing conductors and conduit, it is important to follow the NEC guidelines for conduit fill. The conduit fill is the percentage of the conduit's cross-sectional area that is occupied by conductors. Exceeding the maximum conduit fill can make it difficult to pull conductors and can also reduce the conduit's ability to dissipate heat. The NEC provides tables that list the maximum allowable conduit fill for different types of conduit and conductors. The ampacity of a conductor is the maximum amount of current it can carry safely without overheating. The ampacity of a conductor depends on its size, insulation type, and installation conditions. The NEC provides ampacity tables that list the allowable ampacities for various types of conductors under different conditions. It is important to select conductors with an ampacity that is sufficient for the load they will carry. Conductors must be protected from overcurrent by fuses or circuit breakers. Overcurrent protection devices are designed to interrupt the flow of current when it exceeds the conductor's ampacity. The size of the overcurrent protection device must be matched to the conductor's ampacity. The NEC provides guidelines for selecting overcurrent protection devices. Grounding is an essential safety measure in electrical installations. Grounding provides a low impedance path for fault current to flow back to the source, which helps to trip overcurrent protection devices and prevent electrical shock hazards. The grounding system consists of a grounding electrode, such as a ground rod or grounding plate, and a grounding conductor that connects the electrical system to the grounding electrode. The size of the grounding conductor must be appropriate for the size of the circuit conductors. The NEC provides detailed requirements for grounding electrical systems. When working with electrical installations, it is important to follow all applicable safety precautions. Always to energize the circuit before working on it. Use insulated tools and wear appropriate personal protective equipment, such as safety glasses and gloves. If you are not qualified to perform electrical work, hire a licensed electrician.